Now we go to the last subtopic for chapter 9, which is inductance and energy. In this subtopic, firstly we need to understand the concept of flux linkage. Second, to understand the concept of self-inductance and mutual inductance. Third, to calculate the inductance value for a given inductor structures. And lastly, to calculate energy of inductance. Inductor is basically the magnetic analog of an electrical capacitor. For a capacitor, it can store electrical energy in the electric field present the medium between its conducting surface. This is what you have learned in chapter 6 and chapter 5. Because the capacitor is basically designed by using a two metal plate of two conductor separated with a dielectric. So the capacitor has the ability to store the electrical energy. For the inductor, it can store magnetic energy in the volume comprising the inductors. For example, the solenoid. This figure shows a conductor will have a few numbers of turns. So this is what we call as solenoid. Where the solenoid carrying a current, so it will create the magnetic flux inside the solenoid. So the inductor can store magnetic energy within this volume, and we can determine the energy stored by using a certain formula as well as to determine the energy density. We will discuss how to calculate later on. Next, we go to magnetic flux. Magnetic flux linkage lambda is defined as the total magnetic flux linking a given circuit or conducting structures. Let's consider a conventional transformer. Basically, a conventional transformer is constructed by using a magnetic material, and then we have a two circuit. The first circuit have the certain number of windings or N, and the second circuit also have a certain number of winding or the turns. If we apply the current I1 in the first circuit, so the flux will be generated inside the magnetic material and it will link to another winding, the secondary windings, via the transformer core. If the circuit has n identical turns, the flux linkage can be determined by lambda equal to n flux m. The unit is Weber turns. This flux linkage will generate current, which is induced EMF, in the secondary windings. The induced EMF will be covered in the next chapters. Next, we will discuss about inductance. Inductance can be expressed as L equal to lambda over I and equal to n flux m divided by I, and the unit is Henry. N here refer to the total of flux loop. The total energy expended in building up the current in the inductor and the magnetic energy stored in the incubator can be expressed using this formula. Energy equal to 1 over 2 Li square joules, or we can calculate by using 1 over 2 the integration of B dot H dV. This is a volume, equal to 1 over 2 integration of mu H square dV. The magnetic energy density omega m is defined as the magnetic energy per unit volume. So basically the omega divided by volume. So what we get is 1 over 2 B dot H equal to 1 over 2 mu H square. Okay, the flux here is basically equal to the integration of B dot ds. It's basically the flux density that passing at certain cross-section area. Next, we will discuss about the self-inductance. Basically, the self-inductance representing the magnetic flux linkage of a coil or circuit with itself. The origin of inductance is based on the flux linkage. Okay, let's consider a toroid with a N1 turns, which is coil 1 and current flow of I1 as. Okay, we see in this figure, we have the current I1 and we have a certain number of turn N1. The magnetic flux in the toroid's core is proportional to current I1. Hence, the flux linkage of coil 1 caused by current I1 is N1 flux 1 is proportional with I1. The constant of this proportionality, L1, is called self-inductance of coil 1. The unit is Henry. So this is how we determine the L. L equal to lambda over I equal to N flux 1 over I Henry. This is a formula to determine the self-inductance. Let's see example 3. This example is about self-inductance of a long wire. The question is, consider a long magnetic cylinder with a permeability of mu carrying a current I in a region for R between A and 0 and A. Find the inductance of the cylinder per unit length. So this is a figure. You have I passing across this surface, and we have the magnetic material of mu, and the radius is A. For the solution, we need to find what is the magnetic field intensity for a region for R less than A. This is the solution for Ampere's law. H equal to IR divided by 2 pi A square in the direction of phi ampere per meter. You have to double confirm this using the Ampere's law. Then, using the formula of energy, we know the energy equal to 1 over 2 Ni square or equal to 1 over 2 B dot H dV, and the unit is joule. So you have to make sure the left hand side equal to right hand side, and you expand the formula into 1 over 2 mu H square dV, and then you bring the 1 over 2 I square to the right hand side. So what left is just the inductance. So L equal to 1 over I square, the integration of mu H square to the volume. So you have to know what is the volume of the cylinder. Okay, for the cylindrical coordinate, the volume is R dr dphi dz. Next, the limit is, for the phi is from 0 to 2 pi, for the z is 0 to L, for the R is 0 to A. When you solve these integrations, so you will obtain the L equal to mu L divided by 8 pi. So the inductance per unit length equal to mu divided by 8 pi Henry per meter. Next, we go to example 4, which is self-inductance of coaxial cable. The question is, consider a long coaxial cable with permeability of mu between A and B, which is dielectric, carrying a current density J in a region of between 0 and A, and surface current at R equal to B. Given that the total current between A and B is equal with the total current on the surface of R equal to B, find the inductance of the cylinder per unit length between A and B. Then, find the total energy density stored inside the coaxial cable between A and B. So this is the situation. We have the current here and also the current on the surface. So what is the inductance between A and B? And the energy stored. That is the question. Okay, the solutions. Right. By using the Ampere's law, the magnetic field intensity between A and B is H equal to I over 2 pi R in the direction of phi, where I equal to J dot pi A square. So because this is the current density, and then passing through the surface of the cylinder, which is pi A square. The flux linkage is lambda equal to N flux M. So because this is not solenoid, so the N is 1. So the flux M equal to the integration of B dot ds, and the unit is Weber. So what is the ds? ds is basically dr dz in the direction of phi. And our B is mu h, which is mu I over 2 pi r in also in the direction of phi. When you do the dot product, so it will cancel out, and then you got mu I divided by 2 pi, and the limit is from a to b 1 over r dr dz. So the z is basically from 0 to L. You have to put the z between 0 to L. So when you solve the lambda here, you got the lambda equal to mu I divided by 2 pi ln b over a L. So the inductance is basically lambda over I. So you got mu L divided by 2 pi ln b over a Henry. Finally, inductance per unit length is L over L, inductance over L equal to mu divided by 2 pi ln b over a Henry per meter. Next, the energy density stored inside coaxial cable between A and B. The energy density, omega m, is equal to 1 over 2 mu h square joule per meter cube. Is equal to 1 over 2 mu h equal to I over 2 pi r square. So you got 1 over 8 mu I square divided by pi square r square joule per meter cube. Right, finally we go to mutual inductance. Mutual inductance involves the magnetic flux linkage in a circuit due to the magnetic field generated by a current in another circuit. Let's consider the same toroid but with another N2 turns on the side 2. So we have another circuit at the side 2. This is coil 2. I1 will produce magnetic flux which will link to coil 2. So when we supply the current at the first circuit, it will generate the flux and link to the second circuit. It will pass through. Mathematically, total flux linkage in coil 2 equal to N2 flux 12 proportional to the current I1. Flux 12 is the linkage flux in coil 2 due to current I1. That is the definitions. The constant of this proportionality, M12, is called mutual inductance of coil 2 with coil 1. M12 is equal to N2 flux 12 divided by I1. Let's see example 5. The mutual inductance of long wire. The question is, two long, straight, cylindrical conductor wire, each of radius A, mu equal to mu naught, are separated by a distance d from center to center of the wire. The conductor are used as a go and return circuit. Show that the total mutual inductance per unit length is L over L equal to mu naught over pi ln d minus A over A. You have to prove this. And this is a figure. Okay, the figure based on the questions. We have a two long wire. Wire 1 and wire 2 is identical. It has the diameter of 2A and is separated by distance d from center to center. Alright, so We have a mutual inductance acting on wire 2 due to wire N and vice versa. Let's say we have a L12 or M12 and we have L21 or M21. This is a mutual inductance based on the another wire. So this is the situation, and we have the current, the same directions, right? Alright, for Ampere's law, the magnetic field intensity between A and D minus A is H equal to I divided by 2 pi R in the direction of phi ampere per meter. While the flux linkage equal to lambda equal to N flux M equal to flux M equal to integration of B dot ds, and the unit is Weber. And also equal to 1 because it's just a long wire. So the linkage flux lambda 12 is equal to the integration of B is equal to mu naught I of divided by 2 pi R in the direction of phi dot dr dz in the direction of phi equal to mu naught I divided by 2 pi. So the limit of R from A to D minus A, and then we have a limit for Z. I forgot to put here. It's basically from 0 to L, where B equal to mu H here. So the lambda 12, when you solve this, you got equal to mu naught I divided by 2 pi ln D minus A divided by A, and we have L here. So the mutual inductance is L12 equal to lambda 12 divided by I equal to mu naught L divided by 2 pi ln D minus A over A Henry. Therefore, mutual inductance per unit length is L12 over L equal to mu naught over 2 pi ln D minus A over A Henry per meter. Sometimes the label is L, sometimes the label is M. It depends on the questions. Finally, total mutual inductance per unit length is the L total over L equal to L12 plus divided by L plus L21 divided by L, because this is basically the same magnitude. So mu naught over 2 pi ln D minus A over A plus mu naught over 2 pi ln D minus A over A. So the final solution is mu naught over pi ln D minus A over A Henry per meter. So this is proven.